Okay, adiabatic process is a process in which no heat is transferred into or out of a system. No heat goes in or out of a system. That is, the product of heat changing in the Q is going to be 0 from the first law of thermodynamics. Law of thermodynamics, we have that the Q equals to du plus the work. Now for an adiabatic process, the Q is going to be 0. No heat flows in or out of the system. Then the internal energy du is going to be the molar heat capacity at constant volume CV dt, and then the work done, there's still work done in the system. So we have du 0 will be change in U plus change in the W. So 0 now gives du is CV dt plus work done is P dV. So let's make dt the subject of formula here. That is, bring P dV to the other part. We have CV dt equals to minus P dV. And from here you have CV dt, last expression is equals to minus P dV. Divide both sides by CV, therefore dt is going to be minus P dV over CV, which is the molar heat capacity at constant volume CV. So call this equation 1. But work done W is P dV. W is P dV. Equation 2. So by gas law, which is equation of an ideal gas, when you are considering 1 mole, PV equals to RT. If I differentiate this using partial differentiation here, I'll differentiate P with respect to V, I'll differentiate V with respect to P on the left hand side. If you differentiate P with respect to V, you're going to have P dV, then plus, again I'll differentiate V with respect to P, V dP. Then on this other part, I'll differentiate T with respect to R, because R is a constant. Differentiation of a constant is going to be 0. So if we do differentiating R with respect to T now gives R dt. Then if we do the other way around, we differentiate a constant, it becomes 0. So we are left with this. Call this equation 3. Now all I need to do now is to put the value of equation 1, which is this dt, into equation 3. Anywhere I see dt in equation 3, I'll put that as minus P dV over CV. So put equation 1 into 3. And what is equation 1? dt equals to minus P dV over CV. That is equation 1. And equation 3, we have it as P dV plus V dP equals to R dt. So I'm replacing this dt with this. So I'm going to have P dV plus V dP equals to R, then open a bracket, that comes as negative P dV over CV, close the bracket. So I can continue with this. This will be P dV plus V dP equals to So we take that as R is ratio of molar heat capacity of gases, which is Cp minus Cv, that is R, in the bracket of minus P dV over Cv, close the bracket. So here you have P dV plus V plus V dP plus V dP plus V dP equals to, open this bracket, you are going to have minus Cp P dV over Cv, then minus times minus you give plus it's going to give plus Cv P dV over Cv. Now one thing is observable here, Cv cancel Cv, then you must remember that but gamma is what? Ratio of Cp over Cv. Gamma is known as the ratio of molar heat capacity between two gases, Cp over Cv. So if we have that, you bring that back here, you have P dV plus V dP equals to, in place of this Cp over Cv, it becomes minus gamma P dV, then plus P dV. Now you have P dV here, P dV on this other side. If we collect the like terms, P dV, if we collect the like term, this P dV here, let's put it here, P dV, collecting the like terms, minus another P dV plus V dP will now be equals to minus gamma P dV. Now this and this is out, we are left with V dP minus gamma P dV, V dP minus gamma P dV. So here we are left with V dP equals to minus gamma P dV. So if we rearrange this, that could give V dP plus, bringing this in, gamma P dV, everything equals to what? 0. Now if I decide to divide through this, divided through what we have here, if we divide through by PV, divided through by PV, so as to reduce this differential, this dP, divide through by PV. If I do that, the first part, I'm going to have V dP over PV plus gamma P dV over PV equals to 0 divided by that 0. So here, V cancel this V, you are left with dP over P plus gamma. P here, cancel this P, I'm left with dV over V equals to 0. So at this point, all I need to do is to integrate. So if you integrate this, I'm going to have dP over P plus integral of gamma dV over V equals to 0. So what we have here is the integral of 1 over P dP plus, bring out the constant gamma, integral of 1 over V dV, everything equals to 0. So integral of 1 over P will give us ln P plus, this will be gamma, integral of 1 over V ln V, then everything equals to integral of this, which is 0, equals to 0, or you can say that is a constant, equals to a constant. So we have ln P and ln V. This is addition of logarithm, so I can just have it as ln, then you multiply these two, okay, ln P plus this gamma. Now according to power law in logarithm, this gamma will come here as power for this, so you can have lane V now raised to power gamma equals to constant. So within these two you have addition, so you pick one of the lane P and lane, then you have PV, multiply what you have there, PV gamma equals to your constant, which we introduce here, which could also be what, lane C. So what we have here is that the lane, which is the natural log, cancel this lane, then you have PV gamma equals to constant. Now PV gamma equals to constant is known as the equation of a reversible adiabatic process. Now this P is the pressure, this is the volume, while gamma is the ratio of the molar heat capacity, which is ratio of Cp over Cv. Remember we said something about R. R is Cp minus Cv. Note that. So this is known as the equation of a reversible adiabatic expression process. So for an adiabatic process, you must know that what, the Q equals to 0 because no heat flows in or out of the system, and then you have this.